Okay, this is the lesson following the lesson on Friday, the 12th of June. So we're going to do the proofs of the 5 tangent properties that we looked at on Friday. Now, the first theorem, I think, was theorem number 14, and it was that the tangent to a circle, so this tangent to a circle, is perpendicular to the radius drawn from the point of contact. In other words, the angle between the tangent and the radius is a right angle. And the converse of that theorem is that the line perpendicular, if this line is perpendicular to the radius at the point where it meets the circle, then this line is a tangent to the circle. Now, we're actually not going to prove that theorem. We don't prove that theorem. We're now going to circle theorem number 14, which is the following, that tangents to a circle, so these two tangents to a circle, from an external point are equal. So I'm now going to prove that theorem. Okay, so these two tangents AB and BC are tangents to the circle drawn from the external point B to that circle with centre O. Now we have to prove that AB is equal to BC. So to start this proof, we are going to join OB, and we are also going to join OA and OC. So that way we've got two triangles here. Okay, now what we know is that in triangle OAB and triangle OCB, we know that OA is equal to OC, and that is because they are both equal radii of the circle with centre O. Okay, now we also know that OB is common, so I'm going to write that down. OB is common. And we also know, just from theorem number 13, that the angle between the tangent and the radius is a right angle. So we know that angle OAB is 90 degrees, and we also know that the angle between the radius OC and the tangent CB is also 90 degrees. So we've got that angle OAB is equal to angle OCB, reason that tangent is perpendicular to radius. Okay, so tangent, I suppose you can write tangent to circle is perpendicular to radius at point of contact. Okay, so now basically what we've got is RHS. So both those triangles are congruent, so therefore triangle OAB is congruent to triangle OCB, and the reason is RHS. And now we can say, well, therefore AB is equal to CB, reason corresponding sides in congruent triangles, or of congruent triangles. Okay, and so therefore we've proven theorem number 14. Okay, just for some examples for theorem 14, we know that AB is a tangent to the circle at point C. Now this is from your booklet, page 22. So it's example A. So AB is a tangent to the circle at point C. Find the value of this pronumeral x. This one's fairly easy. We can say that angle OCA, well, it actually is OCB as well, but we need OCA in here. So angle OCA equals 90 degrees, and the reason is tangent to circle is perpendicular to the radius. Okay, all right, and now we can just say, well, therefore x equals 180 minus 90 minus 48, which is 42 degrees, reason angle sum of triangle OCA, okay, equals 180. Okay, and that's the first example there. Now on page 23 of your booklet, it says a circle with centre O and radius 10 centimetres has a tangent AB drawn to it where OB equals 26 centimetres. Find the length of AB. So again, we've got a radius and a tangent to the circle, so we can say that angle OAB is equal to 90 degrees. I can just put that in. Reason tangent to circle is perpendicular to the radius through point of contact. And now with this one, we need to work out the length of AB. AB is the shorter side of that right angle triangle, so we can just use Pythagoras' theorem. So AB squared will be hypotenuse squared minus the other shorter side squared. So AB is going to be the square root of 26 squared minus 10 squared, which is the square root of 576, which is 24. So therefore AB is equal to 24 centimetres. Just making sure that those units are the same before you start that question. Okay, this was Circle Theorem 15. We're now on page 24 of the student booklet. And the theorem was for the touching circles that when two circles touch, the line through their centres passes through the point of contact. So remember, here we've got external contact of the small circle with the big circle, and here we've got internal contact of the small circle with the big circle. So I'm actually going to prove that now, so you can do that in your book. Okay, so to prove this, I'm going to draw the tangent to the circles at point C. So remember that C is the point of contact between the two circles, so they do have a common tangent. So I'm going to draw tangent AB to the circles at C. So what I know is that angle OCA equals 90 degrees, reason that the angle between your tangent AB and radius OC is equal to 90 degrees, okay, through point of contact, which is C, okay? And we also know that angle, so I'm just going to put that that's a right angle. We also know that angle OCP equals 90 degrees, and it's also similarly that your tangent AB is perpendicular, tangent AB is perpendicular to CP, basically, through point C. Okay? So therefore we've got two right angles there, and so therefore angle OCA plus angle OCP is equal to 90 plus 90 degrees, which is 180 degrees. Therefore OCP is a straight line. And obviously, if OCP is a straight line, it is the line drawn through the centres of the two circles, and it actually happens to pass through the point of contact C, because C is the common point of contact of both circles. So therefore, the line through the centres O and P passes through the point of contact C for this particular circle. Okay, looking at page 24, question 1. Now these two circles touch internally at A, and the largest circle has centre O. So we have to prove that triangle ABC and triangle OAD are similar. Okay, well, we have to prove that, like I said, that triangle ABC and triangle AOD is similar. Here we can see that these two circles are touching at point A, and therefore we know that the line through, and we've actually got internal contact here, we know that the line through the centres of the two circles, now we know that O is the centre of the large circle, but we can now say, I'm going to call this, say, point P. I can say that P is the centre of the small circle, because when two circles touch, the line through their centres passes through the point of contact. So we need to state that first. We need to say in part A, so for part A, we say that P is the centre of the smaller circle. Okay, I'm going to call it the smaller circle ODA, because that circle, smaller circle, passes through the points ODA. The large circle would be called circle, for example, ACB, or circle ABC. Okay, so P is the centre of the smallest circle ODA. Reason is because when two circles touch, the line through their centres passes through the point of contact. Now, obviously, to prove that these two triangles are similar, we're looking for equiangular. Now, we actually do not know that CB and DO are parallel, so you can't go stating that, which is why we needed to say that P was the centre of the smaller circle. We know, for example, now that in triangle ABC and triangle OAD, that, for example, angle A is common, so we can say angle DAO is equal to angle CAB. Reason angle A is common, okay? But for equiangular, we're going to need, I'll just put that there, for equiangular, we're going to need another angle. Now, we do not know that these lines are parallel, that CB and DO are parallel, so we're going to have to come up with something else. And because we know that OPA is a diameter of the circle, and so is BOA, that's a diameter of the larger circle, we know that angle ODA is equal to angle BCA, which equals 90 degrees. The reason is that the angles in a semicircle are right angles, and this is because we know that we've got OA is diameter of small circle, and that BA is the diameter of the larger circle. Okay, so therefore we can say that triangle ABC is similar to triangle AOD, and the reason is equiangular. Okay, so that's part A. We now have to prove in part B that CB is parallel to DO. And we've already got that actually, because angle BCA and angle ODA are both equal to 90, and they're also corresponding angles. Therefore, we can say that CB is parallel to DO because corresponding angles are equal. So we're going to start with that. Angle BCA is equal to angle ODA, which both equal 90 degrees. And we can say angle BCA is a corresponding angle to angle ODA. So therefore CB is parallel to DO, reason corresponding, so we've got that the corresponding angles are equal. Okay, now for part C, which is to prove that BC is equal to 2 times DO. Okay, now, part C. If we say that OA is the diameter, so this is an O. OA is the diameter of the small circle. Okay, and that AB, which is equal to OA plus OB, which is equal to 2 times OA, is the diameter of the larger circle. Reason is that OA equals OB. Remember, we've got equal radii there, that OA and OB are both radii. So therefore we can say that AB, the diameter of the large circle, is 2 times OA, diameter of the small circle. So, and because we know that the two triangles are similar, we can in other words, if we say that AB is equal to 2 times OA, then we can say that the ratio of AB over OA is equal to 2. In other words, it's 2 to 1, okay? Because AB is twice the size of OA, then the ratio, if we put the OA down here, the ratio of AB over OA is 2, which really means 2 over 1. Now, because we know that triangle, I just have to show it a bit better. Because we know that triangle OBC and triangle OAD are similar, we know that the ratio of corresponding sides will be in the same ratio. Now we're trying to show that BC is 2 times DO. So I can do that, well, the ratio of BC over DO will be equal to the ratio, or actually I should really put DC to OD, and I'll just fix that. So the ratio of BC to OD is equal to the ratio of BA over OA, and we know that that ratio from up here is 2 is to 1. So therefore BC over OD equals 2 over 1. Oh, the reason for this is corresponding, sorry, one sec. As I was saying, reason is corresponding sides of similar triangles will be in the same ratio. So therefore BC over OD equals 2 over 1, or in other words, that BC equals 2 times OD, which is 2OD, which is what we were required to prove. Okay? Okay, this is the proof for circle theorem number 16. If you can do this in your exercise book, please, that the angle between a tangent, so tangent to AB, and the chord CE through this point of contact C, that angle formed there is equal to the angle in the alternate segment. So what we really want to prove is that this angle between the tangent and the chord, which is angle ECB, is equal to the angle formed in the alternate segment, which is angle EDC. So that was what we're proving there. Now, to do this proof, we need to draw in the diameter CF and also join EF. Now, if CF is a diameter, it obviously passes through the center of the circle O. So we've drawn in the diameter CF, and now we're joining E to F. Okay? And we're also letting angle ECB equal X. Okay. Now that we've got a diameter of this circle CF, we therefore know that angle, we've got a few things here, that angle FEC is 90 degrees. We also know that because OC is a radius, that OC is perpendicular to the tangent to AB, so we also know that angle BCF, or angle FCB, is also 90 degrees because the tangent is perpendicular to the radius. Okay, so we're going to do that now. So we've got angle FCB is equal to 90 degrees. Reason tangent AB is perpendicular to the radius OC. That should be fine, which is at the point, through the point of contact C. Okay, so we've got a right angle in there. Now, we also, if that's a right angle and this angle here is X, we also therefore know that therefore we could say angle FCE is equal to 90 minus X. Again, you've just got complementary angles there. So complementary angles, okay? So this angle in here would be 90 minus X. I won't actually, I'll put that in, but I'll just do it in red. So therefore this angle in here is 90 minus X, okay? Now we also know that angle FEC is also equal to 90 degrees. Reason angle in a semicircle is 90 degrees. The reason is that FC is the diameter. Okay? Okay, so we've got a right angle there. So therefore we can say that angle, because this is 90 minus X and that's 90, we can say that angle EFC is equal to 180 minus 90 minus the 90 minus X, that bit drawn in red, which is 180 minus 90 minus 90 plus X. Oops, I'm just running out of room, which I'll just refocus this. So again, angle EFC is 180 minus 90 plus X, which is equal to X, okay? Well, actually, I'll just put it down there. So it's equal to X. So angle EFC is equal to X. Now, I'll just put an X in there. So now we've got angles in the same segment, or angles at the circumference subtended by the same arc, by the same chord CE are equal. So I can now say that angle CDE is equal to angle CFE, which equals X. I can either say, sorry, the reason for this one up here as well, I didn't put that down, is angle sum of triangles. So I'll just do that now. So I've just put here the reason for this was angle sum of triangle, and you can put triangle FEC. Okay, so angle sum of triangle FEC. Okay, bit hard to read, but it's fine. Okay, so angle CDE equals angle CFE equals X. Those two, they are angles at circumference subtended by the same arc, no, not the same arc, the same chord, CE, are equal. And so therefore we prove that this is X, and now we can say, well, therefore angle ECB, just need a bit more room, angle ECB is equal, so that angle there, ECB, is equal to angle CDE, which is equal to X. Okay, and so therefore you've proven that the angle between the tangent and the chord is through the point of contact is equal to the angle in the alternate segment. Okay, now we're going to do some examples. Okay, this is page 25, and we've just got that theorem up there that the angle between a tangent and a chord through the point of contact is equal to the angle in the alternate segment. Now we're just coming down to these examples down here, and you have to find the value of the pronumerals, and of course we are going to give reasons. So for the first one, we can see that the angle between the tangent PQ and the chord BT, which is 70, equals the angle in the alternate segment, which is alpha there. So alpha equals 70. Reason, angle between tangent, and you may as well put which tangent it is, tangent PQ and chord BT equals angle in alternate segment. Okay, and also we can see that the angle between the chord PQ, angle between the tangent PQ and the chord AT, that's that 50-degree angle, equals the beta, which is the angle in the alternate segment over there. So beta equals 50 degrees similarly, but we've got tangent PQ chord AT this time. Okay, all right, with question B. Okay, have to find the value of the pronumerals again. We can see that ET is a tangent and ST is a chord, so the angle between that tangent and that chord equals this angle alpha in the alternate segment. So alpha equals 60 degrees. Reason, the angle between your tangent ET and your chord ST equals your angle in, I'll just write angle in alternate segment. Okay, now just looking at beta as well, just have a look at that in a minute. Okay, we know that beta is this whole angle there, and this angle 60 degrees is that whole angle. So beta is actually angle EST, and this 60-degree angle is angle ETS. Now we can see that we've got that ES and ET are tangents to the circle. Now they're both drawn from the same external point E. So therefore we can say that ES equals ET, because tangents to circle from the external point E are equal. So we know that ES is equal to ET. So therefore we can say that angle EST is equal to angle ETS. Reason, they are sides opposite, sorry, they're angles opposite equal sides, or we can say, well, we've got an isosceles triangle now. So base angles of isosceles triangle EST. Just move down a bit. So base angles of isosceles triangle EST are equal, because we know that ES equals ET, and that ES equals ET, which is 60 degrees. Reason base angles of isosceles triangle are equal. So therefore we've got that beta, which happens to be angle EST, is equal to angle ETS, which is 60. So we've worked out beta and we've worked out alpha. Now we know that gamma, beta, and 60 are in the one triangle, so we can say that gamma is 180 minus 60, which is 60 degrees, and reason that's just the angle sum of triangle EST. Okay, so therefore all three angles there are 60 degrees. Make sure you put in all the reasons. Okay, now we're going to look at question C on this page. I'm just going to get a little bit of room down here. Okay, blot that out, and this. Okay, let's get started. All right, question C. Okay, you've obviously got a tangent to the circle. We've got a chord there. ST is a chord. PS is a chord. So you've got that this angle beta equals angle alpha. You've got that 72 here. The angle between that tangent and that chord equals this angle up here, which has no label. We've also got another tangent here, GTE, and a chord PT. Well, that 64 equals that angle over there, which equals angle PST. So we've got a lot of angles between tangents and chords. And you're obviously going to have to find some of the pronumerals that aren't listed in that question. So I think if we know that this is 64, therefore that's 64, you might, before you do the question, start putting some things in. So if that angle between tangent GTE and chord PT equals this angle in the alternate segment PST, you've got basically a straight line here. You can therefore work out beta, okay? And then once you've worked out beta, by doing angle sum of straight line, you can work out alpha, which is the angle in the alternate segment between that tangent and, angle in the alternate segment, because we've got this tangent and chord there, therefore beta equals alpha. You can work that out, and then we'll just look at how we're going to work out gamma in a minute. Okay, so let's start with working out, doing the working out for that red 64. So we've got angle GTP is equal to angle PST, which equals 64 degrees. Reason the angle between, and you need to put which tangent we're talking about, because there are like 2 tangents and 3 chords here, so you need to state which tangent. So the angle between tangent, you can go GE, and chord PT is equals the angle in the alternate segment. Okay, so that's that first one. And then you can go that beta is 180 minus 64 minus 72. I'll just work that out in a minute, which is 44. And the reason you've got angle sum of straight line. Now you can't use supplementary angles because there's more than 2 angles there. So angle sum of straight line, and the straight line is, can't really read that, I think it's ESF. Okay. Okay, so we've worked out that 64 there, and we've worked out beta. Now we also know that beta is equal to alpha, which equals 44 degrees. Reason the angle between the tangent, you can even go tangent ES, you don't have to say EF. Angle between tangent ES and chord, and the chord ST equals angle in alternate segment. Okay, So we've worked out beta and alpha, okay? Actually, I should probably put here alpha equals beta equals 44. I don't think it matters, but okay. And now to work out this last bit, we've got to try and work out gamma. Okay, there's actually a few ways we can work out this gamma. We can see that beta plus gamma are equal to angle GTS, because angle GTS is the exterior angle of triangle STE. So that's one way of doing that. We can work out angle PTS by angle sum of triangle here. We can also, and we can just do that by subtracting, we can also say that this angle 72 here equals this one in here, 72, because angle between tangent and chord equals angle in the alternate segment. We can also say that there are many different ways we can do this. We can say that SE is equal to TE because tangents to an external, from an external point to circles, to a circle are equal. So we can say that SE equals TE and that this angle beta equals angle STE, base angles of isosceles triangle, and then work out gamma by doing angle sum of triangle. So there are so many. Okay, now I've just had to cut the video a bit because of a little mistake. So hopefully it's not very disjointed. Now I did explain a few ways of working all this out in the end. I've just decided to go with the simplest method now. So we need to work out gamma now. So we can see that this angle here, so angle, the angle between the tangent FS and the chord PS is equal to angle PTS. So angle PTS is equal to, actually I'll say that angle PSF is equal to angle PTS, which equals 72 degrees. Similarly, because that last reason down there, angle between tangent and chord equals angle in alternate segment, we're doing similarly the same reason, but with tangent FS and chord PS. That equals the angle in the alternate segment there, which is 72. And we now know that angle GTS is equal to 64 plus 72, which is 136 degrees, because that's just the sum of those two angles there, GTP and PTS. And so therefore gamma is, so gamma plus beta is the sum of those, which is 136, or gamma is 136 minus this beta, which is 44, which happens to be, I think, 92 degrees, I hope. I think, yes, it is, because the exterior angle of triangle STE, this exterior angle here, is equal to the sum of the two interior opposite angles. Okay, so that's question C on page 25. Okay, now we're on page 26 of the examples, and you have to find the size of angle X and Y. Okay, we can see here we've got a tangent and a chord, so that angle X is equal to the angle in the alternate segment, which happens to be Y, or it actually could also equal this angle up here that I've marked just there. Okay, so we can actually work out what this angle just here is by angle sum of triangle there, so we'll start with that. So we've got that angle CBA is equal to 180 minus 95 minus 50, which is 180 minus 145, which is 35, I hope. Reason angle sum of triangle CBA. Okay. Now that we know, I'm just going to mark it in, that this angle in here, we've just worked it out to be 35 degrees. Therefore, we can say, actually, we can work out the Y as well now. We can say, well, Y is also equal to 35 degrees. Reason, angles at the circumference. Okay, so we know that 35 equals Y. Angles at the circumference subtended by chord EA are equal. You could have also said that angles in the same segment, that you've got angles in the same segment are equal. And now for the last bit, we can say that angle EAF is equal to angle EBA, or you could have put that it's equal to angle EDA, which equals 35 degrees. Reason, angle between your tangent, now your tangent is AF, and your chord EA, okay, equals your angle in the alternate just make some more room here. It equals the angle in the alternate segment. Okay, and that's that question done there. So we've worked out what x is, because x equals angle EAF, and we've worked out angle y. Okay. Okay, here is question 2 on page 26. And it tells us that PTQ is a tangent to the circle, and you have to prove that BT is equal to BA. Now we know that the tangent to a circle, the angle between the tangent and the chord is equal to the angle in the alternate segment. So we'll just start with that. So we've got that angle QTB is equal to angle TAB, which equals alpha. Reason: the angle between your tangent, and you can call it just tangent QT, and your chord BT equals your angle in the alternate segment. Okay, so now I can mark that this angle here is also alpha. Okay, now we're trying to prove that BT is equal to BA. Now we know that angle BTA is equal to angle BAT, which equals alpha. So therefore we can say that BT is equal to BA because they are sides opposite equal angles of isosceles triangle. Actually, I can say therefore triangle TAB is isosceles up here. So I can say BT equals BA, sides opposite equal angles of isosceles triangle are equal. Okay, and therefore we've just proven that BT is equal to BA. Okay. Okay, this is our last theorem, number 17, and we're going to prove it. And the theorem is that the square of the length of the tangent from an external point, so PA squared, that's the tangent, PA, is equal to the product of the intercepts of the secant. Now the secant is PC, so the intercepts of the secant are PB and PC. So therefore PA squared equals PB times PC. Please be very careful not to do PA squared equals PB times BC. It is not that. It is PA squared equals PB times PC, because it's the intercepts of the secant passing through the point P. So each of these secant points must have a P in it, PB and PC. Okay, now to prove this theorem, we are going to join AB and AC. Okay, now we know, actually I might just do it as a dotted black line. Okay, we know that A is a tangent, PA is a tangent, so we just need to remember that. Okay, so join AB and AC. Now if we're going to prove that PA squared equals PB times PC, we're obviously going to need to prove that triangle PAB is similar to triangle PAC. So we'll start with that. So in triangle PAB and triangle PAC, now I don't know if they are written in order, because I'm trying to prove that they're similar, but I don't know the order yet. All I know is that angle, let's say APB, would equal angle APC, which then the reason is that it's common, or I could just say that angle P is common. Okay, reason angle P is common to both. Okay, so I've got this common angle in there. Now I also know that PA is a tangent, so this angle here, the angle between the tangent PA and the chord AB, is equal to the angle in the alternate segment, which is angle ACB. So I can also say that angle PAB is equal to angle ACB, and the reason is the angle between the tangent AP and the chord AB equals the angle in the alternate segment. So therefore we've got enough in that triangle. We've got equiangular. Therefore triangle APB, which is arc dot blank, is not equal to, is similar, I'll just fix that up, is similar to triangle. Now let's get the order right. Arc dot blank. I need in the big triangle arc dot blank, so it's similar to triangle CPA. Reason, equiangular. Now that we know that the triangles are similar, we can do corresponding sides of similar triangles in the same ratio to show, to prove this theorem. Now we're trying to prove that PA squared is equal to PB times PC. So I'm going to draw these two triangles out separately. I've got APB, the dot here and the arc there, and I've got the large triangle there, and I've got C there, A there, and P here, so I've got the dot there. Now the sides that we need to be using, we're trying to prove that PA squared is equal to PB times PC. So when I do my ratios, I don't want to be using side AB and side AC because they don't appear there. So let's just try and use the sides PA, PB, and PC. Okay, so let's go from small to big triangle. So I know that in the small triangle that PA, that's dot and dot arc, matches with this one over PC is equal to, I need PB in my proof, so it equals PB, which is dot blank, and I need dot blank here, over PA. And the reason for that is, and we've got reason for that is corresponding sides of similar triangles in same ratio. Therefore, because we've got fraction equals fraction, we can cross multiply. PA times PA equals PB times PC, or PA squared is equal to PB times PC. Okay, and so therefore we have just proved that theorem. Okay, now we're going to do the last few examples. Now I'm on the final page of the booklet, page 27, and you have to find the value of the pronumerals. So we can see that DC is a tangent, and the secants, the intercepts of the secants are CB and CA. So we know that DC squared equals CB times CA. Reason is the square of the tangent from an external point C equals the product of the intercepts of the secants passing through C. Okay, so we can just substitute in the values there. DC squared, sorry about that. So DC squared is 6 squared, and CB is X, and AC is X plus 5. So we're going to have to expand this bracket. So we've got 36 is X squared plus 5X. Therefore, we've got a quadratic here. X squared plus 5X minus 36 equals 0. Factorizing that, you would get X plus 9, X minus 4 equals 0, because we get X squared minus 4X plus 5X minus 36 is 0. Therefore, X is negative 9 or X is 4. But we know that X is a length, so it must be greater than 0. And so therefore, X equals 4. Okay? And if we have a look at that, and if X is 4, 6 squared is 36, and 4 times 9, remember it's CB, which is 4, and CA is 9, so 9 times 4 is also 36, so that works. Okay? Now looking at example B. Okay, this is our very last example. Okay, we've got that BA is the tangent, and the secant intercepts are BC and BD. So we know that BA squared is equal to BC times BD. Reason, the square of the tangent from external point B equals the product of the intercepts of the secant passing through B. Okay, substituting in the values, BA is x, so x squared equals 1.7, which is BC, and BD is actually 1.7 plus 1.6, which is 3.3, okay? And working that out, we get that x squared is, I'll just get my calculator out, and so when we do we put those in, so x squared is BC, which is 1.7 times 3.3, which is 1.7 plus 1.6, okay? We get x squared is 5.61, therefore x would be the square root of 5.61. Now it'll be the positive square root of 5.61 because x is a length and it has to be positive, so therefore it's the positive square root, remember it was the positive square root of 5.61, which is 2.368, and because this is given to two significant figures, I'm going to give my answer here to two significant figures, which is rounding it off to 2.4 centimetres. Okay, girls, and look, that's the end of the booklet. So I'll just write down now what the homework is from exercise 9.4. Okay, girls, if you could do all of exercise 9.4, really sorry about that. It's just because it seems to use a lot of the different theorems. Even if you don't physically write down some of the ones that are quite easy, if you just look at it, work out the value of the pronumeral and know the reason, but it actually would be really good practice to write it down because then you're practicing writing the proofs over and over again. So exercise 9.4 all. Thanks, girls. That's the end of the video and the end of all the theorems and the proofs. Okay?